In software engineering, a monolith is a single-tiered application in which the user interface, the business logic, and the data layer are all combined into a single entity, which means that all the functionalities of the software are bundled together. This type of architecture is often used when the product is at an early stage and the team of engineers is quite small, each member of the team sharing the knowledge and the accountability for both the front end and the back end. By opposition, in a high-performance organization, it's usually common to find multiple teams, each team being long-lived, autonomous, and cross-functional. Consequently, an organization composed of loosely coupled teams requires a loosely coupled architecture, and such architecture is known as the microservices architecture. I'm Raz, and you're watching Explain It to a Duck. In essence, the idea behind microservices is to break down a monolithic application into smaller, loosely coupled and isolated components called services, each service meeting a very specific business need, like for example, handling payment methods, sending emails, or managing customer accounts. Here, loose coupling means and implies a few things, and the first thing being that components should depend on each other to the least extent practicable by sharing the minimum degree of direct knowledge that one has over another. Unlike in the monolithic architecture, components or microservices are not supposed to know the inner workings of other components. All they need to know is how to call them through their API, which indeed makes a lot of sense, since it's not code internally calling code, but it's services calling other services over the network through protocols such as HTTP or AMQP, for example. And because of that, it becomes fairly easy to occasionally replace components with alternative implementations that provide the same service through the same interface, introducing little to no breaking changes inside the existing codebase. In short, loose coupling brings the system to be more efficient and more flexible, as it allows links between components to be broken or easily reconfigured. It helps coping with the load by spawning multiple instances of the same service if under too much stress without having to scale up the whole infrastructure, and it promotes the implementation of new ideas by letting you freely choose the right technological stack or framework for each service. Which brings us to the next point, isolation. And when we talk about isolation, we have to consider 4 dimensions: space, state, time, and failure. The isolation of space means that microservices are deployed independently and executed within a separate process, like on Docker, for example, where each service runs in its own container. It allows each service to be started, stopped, redeployed, or scaled independently without having to take down the whole infrastructure, and also to push to production features and bug fixes much faster, as indeed one update is usually local to one or a few services and not the whole infrastructure. The isolation of state refers to a microservice being fully responsible for its persisted data. Any access to the data from the outside is made through the service API, creating in a way a firewall that prevents the data from being corrupted or modified without the service being aware of the change, which also allows each service to freely choose which technology to use in order to persist its state without having to adapt to its consumers. The isolation of time refers to a microservice limiting its synchronous calls only to services that respond quickly. Since components are not located in the same process, making long-running asynchronous calls through a message bus such as RabbitMQ, for example, enables the caller to avoid idle wait time by firing several calls at once instead of sequentially, ultimately improving resource utilization. And finally, the isolation of failure, also known as resilience, means that if one or more services crash for some reason, the rest of the application will still be running. Indeed, in the monolithic architecture, it's quite common for a single failing component to bring down the entire application if an error is not properly handled. But since microservices are running on different processes, if one goes down, it would only become unavailable to its consumers without spreading the error across the system. But all these advantages comes at a cost, and it's the one of complexity. Without going too much into detail, let me give you a brief overview of the challenges associated with this kind of architecture. And the first one being the technological spread. While each microservice has a smaller code base and is simpler in essence, there's now a potential need of maintaining multiple technological stacks, multiple projects, and multiple documentations for each one of them. With that comes the fact that we need to ensure that each service is properly connected to its own deployment pipeline for continuous integration, delivery, or deployment. If you don't know what that is, I suggest you watch the video I made on it. Testing also becomes much more complicated, and especially if there are many dependencies between services. As compared to a monolith, where most of the calls are made internally, now the same calls are made over the network. And speaking about network latencies arise as a new problem too, as we now have to plug extra communication mechanisms between services, whether it's stateless like HTTP or synchronous like AMQP. If not carefully designed, each latency on each network call could compound and completely throw your system off balance. And finally, data integrity becomes a true headache. Some actions performed on the application may require calling multiple services that will perform multiple business transactions, resulting in multiple database operations, which requires an eventual consistency of data or very complex rollback mechanisms in order to make sure that the system is at a coherent state at all times. And that wraps it up for today, guys. Feel free to share, like, and comment this video if you find this content useful, and see you in a week for another episode of Explain It to a Duck. Cheers!